our next young speaker, Karthik. He works in Minio, and he's also part of FSM. Who knows what FSM is? What is FSM?
FSM, Free Software Movement.
The Free Software Movement. Okay? If you all want to know more details about FSM, definitely contact Karthik. Yeah. Interestingly, our man's just recently joined, and he's already holding his hands. No, Gautam, please don't. He just joined Shankar Mahadevan's Music Academy and is learning how to sing. So he shall sing his presentation to us. Over to you, Karthik.
Yeah, thank you. So, so as you can see now what the topic is, but post-lunch sessions are always hard, not just for me, but for all of you guys too. But I'll try to keep the talk, really simple and really general so that it can appeal to people who are really new to Go, and also might be if there are people who are really new to programming too. I just want the talk to still make some sense. Keeping that in mind, I've kept things really simple. Now, before starting with what Go routine leaks are, and why should you even bother about Go routine leaks? And if you're a Go developer, why is that you need to take it seriously? At least consider it as important. Let me start with some fundamentals, to give you a background check on where this problem originates from, so that you can weigh the problem considerably good enough so that you don't underestimate the issue that can be caused by Go routine leaks. To begin with, we know what concurrent programming is, right? And why do we do concurrent programming, right? It's now you have, instead of executing, having a sequential stream of execution, now you have multiple sequential streams of execution which can execute your program and achieve your computations faster and can make use of your processing abilities better. And that's the reason why concurrent programming now in today's software development is no more an option, right? It's really necessary that you make use of your hardware capabilities to be able to achieve your computations faster. Okay, now we know concurrent programming is really important, and one of the selling points of Go is that Go makes concurrent programming really easy. And if you're new to Go and if you've been hearing and exploring about Go, and even today at GopherCon, you might have heard this like a lot of times, right? Concurrent programming in Go. Go makes concurrency, concurrent programming easy, and language comes with fundamental bindings which makes it, easier than any other language has concurrent programming, whatever it offers to you. Now, okay, that sounds good. We know now that concurrent programming is important. It's necessary in today's software development. And now, we also know that Go makes concurrent programming really easy. Go achieves that by giving you this primitive called Go routines. What are Go routines? Go routines are analogous to lightweight threads. Now, we know about threads, right? Threads are fundamental building blocks of parallel or concurrent programming in general. That's cool. Again, to sum it up, Go makes concurrent programming easy. That sounds good. Let's begin concurrent programming in Go. But what is that you need to watch out for? When you begin writing concurrent software in Go. Yes, we need to synchronize, right? Synchronization is not very specific to Go routines or Go in general. Right? When multiple units work together towards a common goal, it's really important that they need synchronization, right? Like in case of these autonomous flying robots, where they need synchronization between each other, communication between each other, so that they can, work towards a common goal, achieving a common goal. And And the same concept applied to programming too, when multiple threads or multiple Go routines, when they work concurrently or parallelly in achieving a common goal, they need to be able to synchronize with each other. Okay. Now we know how synchronization in parallel programming works. What is the synchronization model? So in traditional programming approach, synchronization is done by shared memory, right? So there's a memory which is shared across multiple threads and they have access to them. And the access to the shared memory is controlled. It's made safer using locks. But Go has a different approach using Go routines and channels towards synchronization, right? Instead of explicitly using locks to communicate or how it in general works with a shared memory model, Go encourages the use of channels, where you just pass the reference of data between the Go routines, and this ensures that only one of the Go routine, that only one of these lightweight threads have access to the data, which gives really a safer way or safer access to the data. Now, okay, this sounds good now. Concurrent programming is easy in Go, and Go routines and channels are the primitives which one needs to use in concurrent programming. And wait, there are instances where the synchronization can go wrong. Synchronization at times may not happen the way you expected it to be. And this could result in some of these lightweight threads, some of these Go routines, blocked, hung forever, because of wrong coordination and wrong synchronization. Yes. This is where leaks comes into picture, right? When the synchronization doesn't happen right, when the communication between Go routines doesn't happen right, and when they are blocked forever, and this is where the leaks come into picture. And why is that you need to worry about Go routine leaks? Because in a long-standing program like web servers, these leaks can accumulate over a period of time, eating up your computational resources, and you may not be even aware that this is happening in the system. Only when you run out of resources, that when you start digging deeper, you might notice that there are leaks in your code. Okay, so now we know that you need to watch out for Go routine leaks when you're writing concurrent software in Go. And what is the root cause of these leaks? The root cause of these leaks usually in general are, if you try to write into channel without a listener listening from the other end of the channel, or vice versa, and this is where primarily the leaks would happen. And this could manifest in a variety of ways, right? Sometimes being not so observant while writing code, even this might lead to Go routine leaks and not having receiver or writer into channel, because of which the Go routine might be blocked forever, resulting in leaks. And rather than now focusing on why exactly leaks happen and what are 100 different ways, 100 bad practices because of which leaks happen, let us focus more on how do we detect that there is a leak in the concurrent software you've written using Go. And how do I detect them? How do I identify that, oh yes, there's a leak in the code? And how do I debug them? How do I avoid them is what the focus of this talk is. Yes, every time you spin a Go routine, you use the Go construct. Be watchful and be aware that how does your Go routine exit gracefully. Just be mindful of this fact whenever you spin out a Go routine, whenever you try to write a concurrent software, whenever you spin out this lightweight thread, be very, very, very mindful and understand, that at any cases, there is a graceful way that my Go routine ends. Being observant most of the times, actually avoids, you can avoid these leaks. Oh yes, here are some of the practices which you can follow. Very simple practices is you can use timeouts for graceful ending of your Go routines, or you can, use the context package. You saw that in the first talk today how context package can be made use of. Okay, now let's say you built your web service using Go, and for better utilization of your resources, you're writing concurrent piece of software, and you do not know that whether there exists a leak. You do not know maybe one of the packages you're using might be having leaks. So it's really necessary that you test your services, test your endpoints before you put it into production to whether there exists a leak. So the first part deals with to actually check, whether there is a leak in your code or in any of the libraries you're using. Are these Go routines accumulating over a period of time, eating up your resources for no reason? So the way to go about this, the first step could be that in your web services, you can add an endpoint, which returns the number of Go routines which are alive in your system. So you can use the runtime.num Go routine function, which is provided by the runtime package, which returns the total number of these lightweight threads that exist in your system at a given point in time. So what you could do is, before you put your endpoints, your web services into production, run a very simple load test. Let's say send 50 concurrent HTTP requests to your endpoint and check whether there is an unusual increase in number of Go routines alive in the system. Okay, this is like a very simple check which can help you understand whether these routines are accumulating indefinitely over a period of time. Yes. So here is like a very simple formula. So have an instrumentation endpoint in your web server which returns the number of Go routines alive in your system. Call that endpoint before your load test to see how many Go routines are alive in the system. And let's say now you bombard your endpoint with 50 or 100 or some number of concurrent requests. And after your load test is finished, again check what are the number of Go routines alive in your system. If you find it really abnormal, then there exists a leak in your code. It might not be in your code, might be in one of the packages you're using. The first step is done. The first step is to identify, oh yes, now there is a leak in my code. Once you identify that there is a leak, how do you actually find or figure out and pinpoint to the origin of the leak? So that comes the next step. So again, having these very simple instrumentation endpoints in your web server is the key. You can have a very simple instrumentation endpoint which returns the stack trace of your web server, right? So now, so the way now you identify the leaks is by sending a request to this endpoint which sends the stack trace, which clearly gives you an idea where the leaks are originating from. Okay. Apart from these instrumentation endpoints, you can identify the leaks with the help of profiling too. A lot of the occasions, some of the Go routines might be indefinitely sleeping due to bad logic, or they might be blocked forever. Or some of these Go routines might be spinning out so much that they're consuming a lot of memory. And usually getting a profiling too gives you an idea of the hotspots in your code. And at times, it might even lead you to a possible leak in your code. Yes. Again, the key is to make sure that you use this instrumentation with inside your code alongside the load test before you put your web services into production. It's only then these leaks magnify, and it will be easy to identify them. Usually, it might so happen that you would underestimate leak of a single Go routine. But in a long-standing program, over a period of time, with number of users to that particular service, it would accumulate and turn into a disaster. So the best way to avoid leaks is to catch them really early. Now, you can have these hooks in your tests, which can identify the leaks in the stages of your unit test itself. rather than to wait and test your endpoints functionally or from outside or from your load test, you can have these hooks in your unit test itself, which can give you an idea of whether there's an existence of leak in your code. So again, the practices which we followed in the load test, the same practice you could follow in your unit test too. You can get a count of difference in number of Go routines in the system in your unit test itself, or a stack difference in your unit test itself, so that if there are any anomalies, fundamentally in the function you've written, they're caught really early, even before you load test them or even before you put them into production. Yes. So safety by design. Now, let's say you couldn't catch a leak during tests. Let's say you missed these leaks even during your load test, and your code is in production, but you sort of suspect that there's some resource outage in your code. And now you try to follow the same steps to see what's the origin of these leaks, or whether there's leaks in the system. And it's really, really hard to do when you have one single bloated binary with all the services merged in. It's seriously hard to debug, and leaks in any one of your services and one of your endpoints can actually cause an outage in all of other services, right? So it's really important that by design, you have followed a microservices architecture, and each of your services run as a separate container or a binary, so that now any outage or any unexpected resource usage now can be caught easily and can be pointed to a particular service, rather than have to now dig through the entire bloated binary and in production, which is seriously hard. Now imagine trying to get the stack trace of your service where the entire service is in one binary. You cannot make sense out of it. But in case if these services are separated and if they're built as different containers, or you follow the microservices architecture, it's really easy to identify the buggy endpoint or a buggy service. And also, it's great if when you go with microservices architecture, that you use the orchestration which is provided by the tools which knows the best on how to do it. So rather than building the orchestration inside your code and making it more complicated and harder to debug and letting your failure domain spread a lot, you can use tools like Kubernetes, Docker Swarm, or even Mesosphere to scale or to orchestrate your web services, so that you can have multiple of these microservice or small endpoints or small services, and you can deploy and scale and manage them really easy. Yes, thank you.
Any questions for Karthik? There you go. We have one question. Right in the middle, please.
In the beginning, you mentioned about the root cause for the leaks, which is the listeners not being present in the channel, or So, any best practices that you could suggest how these checks can be made and this is avoided?
Oh yes. So, what we have experienced is now. There are a variety of ways wherein sometimes even a bad logic could even result in having a listener like stranded or blocked forever. It's seriously hard to tell that this exactly would be the reason why you did it wrong. But some of the best practices which I mentioned was like having timeouts in your for select loop, wherein if a go routine is unattended for a while, if it's blocked forever, it just times out. And also using context package throughout your code to make sure that if there is an abrupt end-to-end endpoint or a service, you can gracefully shut down all other Go routines, or you can even time out them. So I think these are the ones which would come to your rescue, so that you don't let this Go routine stranded.
Thank you.
Yeah. But I think it's really important that now, since it can manifest in various ways, as I said, even a bad logic could do that, it's important that you do this instrumentation within your code before you deploy it. So that's when you will realize, okay, these are the variety of ways where I got it wrong.
Okay, we have another question there, please. Somebody did raise their hand there, right? Yeah.
Yeah, so you have suggested load testing to identify the leaks, right?
Yeah.
And one of the way which is very good to find out the leaks is that the number of Go routines increase the number. Other ways which we can identify that there's such kind of leaks like more CPU utilization or anything.
Yeah.
So how we can look at our performance testing results which will let us know, help us identify such kind of things?
As I said, so one of the other really useful tool is to profile your code with load, right? So profiling is even possible by writing unit tests and using them. But I think you will get more useful result if you subject your endpoint to load, like let's say 100 or 1,000 concurrent requests, and then take the CPU profile, then take the Go actually gives you the facility to take this profiling in a really easy way. And you can take these profiles, memory profile, CPU profile, or block profile, and then you can identify the hotspots, those pieces in the code which is actually consuming most of your resources, and then you can narrow down and dig deeper and see why is it consuming so much of resources. Yeah.
And we have the questions piling on. One more. And the last one, please.
Hi. Could you explain what block profiling that you have referred in PPT?
Oh, yes. So we understand CPU profile, right? So you'll be able to see what percentage of the CPU is being consumed by specific functions. There'll be, boiled down function by function or the hotspot line by line. Memory is also obvious. So block profile is, so when you're trying to coordinate between these Go routines, as I said, the issue is that some of them might be blocked indefinitely, right? Which is not doing any computation at all. It's just wrong coordination, right? And these are the kind of, this is also a resource outage, right? Now, these Go routines are consuming resources, but they're not doing any computation now. So such issues can be identified by block profiling. So whichever Go routines that are blocked, and these are also hotspots which are wasting your resources now, those can be identified using block profile.
Okay, thank you, Karthik.
Yeah, thank you.
I think we'll run out of time on this.
I'll be around. Also, I have published the blog on the talk with more detailed code with load tests or simple examples with leaky servers, so you can just check that out.